welcome to the Joy of Abstraction book club, chapter 8. And this is the chapter where we actually get to see the definition of a category. And that makes me very happy that we're getting to this point in the book club, and there are loads of questions this time. So I'm quite excited. I've been traveling this week and I did not manage to find enough time to make the video while I was away because there are 24 questions. And I'm really glad. So I guess we'll just start. So thank you to everyone who submitted questions. Thank you for everyone who's watching. Thank you to everyone at the Topos Institute for sorting out this book club. Thank you to the weather, which has now turned warm, which I really like. It's actually summer in Chicago now. We don't have spring. We just wildly oscillate between winter and summer for a bit. So that's what we're doing now. It might well snow next week. Right, the definition of a category. First question is about the relationship between, okay, that's too many words, relationship in here, category theory and equivalence relations. And so it's a comparison between the relationships in category theory and those in equivalence relations from the previous chapter. So what I've said is that equivalence relations are true-false. Well, all relations are true-false situations, yes-no situations, whereas category theory are not that and are more nuanced. And so the question says, can I explain how category theory relationships are less yes and no? So thank you for that question. I hope that this will become more clear as we go along and see more examples of categories. So perhaps in the next few chapters in the tour of math, where we're seeing different actual examples of categories, you'll see what I mean by it being less black and white and yes or no. But the point is that when you've got two objects in a category, there can be loads of morphisms between them. Whereas when there's a relation, you either do or don't have that relation between those two objects. So if we're looking at the relation less than or equal to, for example, a pair of objects A and B, A is either less than or equal to B or it isn't. Whereas for categories, you could have loads of relationships between A and B. For example, if A and B are sets, there are loads of possible functions from A to B. Or if A and B are points in a space, there are loads of possible paths from A to B. Or if we thought about family relations, or just relations, not family relations, relations between people, then there could be various relations between A and B, because A could be the mother of B, but could also be the piano teacher of B, and could also be the math teacher of B, I suppose. And so a more black and white situation for that would be just whether A and B have any relationship at all. So if they either know each other or they don't. But then we start talking about how they know each other and things become more nuanced. So we'll also see that symmetries of objects can be regarded as a form of relationship. And so if an object has a lot of symmetry, then it will have a lot of ways of relating it to itself. So for example, if I take a rectangular piece of paper, then one of its symmetries says, if I hold it like this and then flip it over that way, it now looks the same. And that's a relationship between it and itself. But I can also do it by flipping it that way. That's another relationship between it and itself. And I can also do it like that. So in a more black and white situation, we might just say, is this piece of paper symmetrical at all? And it either is or it isn't. But then we can ask in what ways it is symmetrical. And now it's got various different ways, because we can do that and that and that. And we can also leave it like that. So that's a little bit about what I mean by there being more nuance with relationships. It's not just, is there a relationship or not? We can express a lot of different ones. So there are often many different morphisms between objects. Okay, I hope that helps a bit. The next question is about page 95. I'm trying to map what you're saying to my understanding of mathematical logic. So when I talk about structures, are these the operations? And if not, what are the operations in the formal definition? When I talk about mathematical structures, I'm not being very technical. I'm talking about mathematical things. A mathematical thing is usually defined in the way that we've defined a category, where you start with some basic building blocks and then you put some structure on them. So you put in some things that you can do with those basic building blocks. And that's why I call it a mathematical structure. You could also call it a mathematical concept, but I call it a structure to emphasize the fact that there are things relating to each other in it. And I don't know what the last part of this question means exactly, because there aren't any operations in the formal definition. So a mathematical structure often does have operations in it, because, for example, in the definition of a monoid is a set with a form of multiplication on it. And that form of multiplication is an operation. And that's what gives the monoid what I would call its structure. But a mathematical structure doesn't necessarily have to have operations inherent to it. For example, a metric space is a set of points with a concept of distance between them. And so the fundamental concept there isn't any way of operating on the points to produce other points. It's a way of relating the points to each other. And I would call that a mathematical structure because it has some way of relating those points to each other. In the definition of a category, we have objects and morphisms, and then we do have some things we can do with those morphisms to put them together to make other morphisms, and that's what makes it a structure. Whereas a mathematical concept, I suppose a mathematical concept could be something like the concept of addition, and I wouldn't necessarily call that a mathematical structure. I mean, addition is a binary operation. I wouldn't call it a structure exactly. It's a bit subtle, but I'm glad that you're asking these things, because these are the kinds of things where mathematicians throw words around sort of instinctively, and they're not necessarily being formal about it, but it can be confusing. But it is a bit like learning to speak English in the first place. If you learn it as a child, then it's not that someone sits down and defines every word for you. You just sort of pick it up by osmosis because people use it. And then maybe sometimes you need specific definitions of things, but that your basic understanding of the language comes from listening to people just using it. Okay, so on the next question, page 98. Gosh, there are so many questions. I should probably tick them off as I do them. Page 98, what do I mean by reading relationships dynamically? So what I say on page 98 is I've drawn the composite as a dotted arrow to remind us that this is the one we added afterwards, deducing it from the others. This is where videos really help with category theory, because the diagrams are often dynamic in that you draw part of the diagram first and you deduce some other part, and then you deduce some other part. And so then I say, here's another example involving some different family relationships. See if you can practice reading it dynamically. So what I mean by reading it dynamically is understanding that the dotted arrow comes afterwards. So let me just share that whiteboard screen again. What we've got in that particular diagram is, here's how I would draw it. Oh, I don't have a pen. Okay, let me try that again. So the diagram looks like this. We've got A is a sister of B. And B, it's a bit wonky, isn't it? Is a mother of C. And then we deduce. Now, see that I'm drawing this last arrow last. And so I'm drawing this arrow dotted to show that it's the one that we've deduced from the other ones. And this makes A the aunt of C. So now, if this were a book rather than a video, all you would see is this picture at the end. And so reading the diagram dynamically kind of means imagining that this had been a video in the way that I just did. So imagining that, first of all, you're just seeing that the the solid arrows, and then the dotted one is coming afterwards. And when we do commutative diagrams, there'll be a lot of places where, because it's a book, I couldn't make the diagram grow in real time. But reading a diagram dynamically means imagining it growing in real time so that you move your way across it in real time, even though the print on the page isn't moving. Thank you for that question. The next question, is it possible for A to be thought of as a generalization of B in one way and B as a generalization of A in another way? I think I'm going to go ahead and say probably, because there's probably a situation in which things are generalizations of each other in different ways. I wonder if you have anything in mind. So that's an interesting example to think about, to see if you can come up with something. I can't come up with anything at the moment, because usually when A is a generalization of B, it completely subsumes B. But maybe there's a way in which you could be really thinking about one aspect of things only. I don't know. Good. Okay, so the next question is about the relationship between composition of arrows and transitivity. So it says, it's about the fact that composition of arrows is kind of, well, the question says harder. I wouldn't say that composition of arrows is harder. I would say it's more subtle than transitivity. And is it the fact that there are two ways of composing with arrows? No, it's the fact that it's really the fact that morphisms are more interesting than relations. So with relations, transitivity is just either true or not. Whereas with composition, you have to figure out what the composite of the arrows is. And let me just take a quick look at what I actually said on that page to make sure that I'm making some sense. So I think that, okay, I think it's at the top of page 98, where I say this is similar to transitivity, but different. Right, so it's the fact that the relations are yes-no situations, whereas now we're in sense in which situations. So, right, what we're saying is there's a sense in which A is related to B, and there's a sense in which B is related to C. What does that produce for us for the sense in which A is related to C? So it's not just a yes-no situation. And I suppose fundamentally, whenever something is not just a yes-no situation, it's going to be harder because there are many more options. It's not just checking whether something's true or false. It's checking what is really going on. So maybe that's why it's harder. Next question. Is associativity to enable long chains of compositions in a category, or to enable associations of composition in a different order? So this is on page 101. And at the bottom of that, page, I say, note that associativity looks like it's a condition on three composable arrows, and it is, but really, what we really want to know is that a string of composable arrows of any length has one unambiguous composite. Right, and so what we're saying, I'll get the whiteboard back again. What we're saying is that associativity tells us what happens if we compose three arrows in a, I don't like using capital letters for objects in a category. So it tells us what happens if we compose three arrows in a row, and that there's one unambiguous way of doing it. But what we really want to know is that if we have any chain or string of arrows in a row, E, F, G, no thanks, no, I don't need that, G, however long it is, there is one unambiguous way of doing it, because you know that associativity tells us that there's an unambiguous way of doing any three, and then we can prove by induction that there's an unambiguous way of doing any string. And so this question asks us if it's composition in a different order. You can't really do composition in a different order, because if you have F going from A to B and G going from B to C, there is no other order in which you can do that composition. You might think about it as doing composition in a different order like this. So if you do this composite first, then you'll get H composed with G. And if you do this composite afterwards, then you get H composed with G composed with F. And so you've sort of done it in a different order because you've composed G with H before you did the composite with F. Whereas if you do the associativity the other way around, I'm pretty sure this was at the end of the chapter, then you have done the composite of F and G first to get G composed with F, and then you do the composition with H afterwards. But I think it's a bit ambiguous to call that composing in a different order because also I apologize that I used F, G, and H here, and I also used it here. So this is not the same notation. This is new notation. It's ambiguous to call it doing composition in a different order because that might mean that you're putting the arrows in a different order. But there is a sense in which it is doing the composition in a different order. I would just be afraid of saying that because I think it's a little bit ambiguous. Okay, good. So the next question is a kind of cute one to read out because it says, how do you pronounce Ob and Hom? Are they pronounced Ob and Hom? And the answer is yes, they are pronounced Ob and Hom. I know we do pronounce things weirdly in math, but I do pronounce them Ob and Hom. Okay, good. Page 102. What's the relationship between symmetry and commutativity? So I'm going to get my whiteboard back again. Symmetry for relations is where we say, so symmetry means for all A and B in whatever set we're thinking of, A being related to B implies B is related to A. Now, if we turn this into a category, I might represent that as an arrow from A to B. And then this one would be an arrow from B to A. And so symmetry is going to be something like saying, if we have a morphism from A to B, do we have a morphism from B to A? And so I could also draw that morphism as the morphism going backwards. And so it's really about the reversibility of morphisms, or perhaps the invertibility of morphisms. Whereas commutativity is about switching the sides in an operation. So commutativity oh dear, I can't spell. Commutativity says for all X and Y in whatever structure it is you're thinking about, X and then some binary operation with Y equals Y and some binary operation with X. And so there is a symmetry in this situation because X and Y are playing symmetrical roles. But symmetry for relations is not really the same kind of thing. Although it looks like A and B have swapped places, remember that this relation is not a binary operation, whereas this one is a binary operation. And so I think that it makes a kind of superficial similarity, but that these are really different things because these are answers and these are statements. And I'm going to pause and think for a second about whether those are analogous in some way. I think they might be analogous because they do look analogous on the screen, but I don't think that that's a particularly helpful way to think about it right now. That's what I will say. Because, let me get that screen back again. Because these ones are statements, and that's an implication, and these ones are objects, and that's an equality, I think it's more important to keep those separate. Think about them separately at the moment. Okay, page 102. How common are categories which are known by multiple distinct names? What did I say on page 102? I'm not sure I said anything very specific there, but maybe it's just about the formal definition of a category. And the answer is that people use various different names for categories. And the important thing is that the name isn't the thing that matters. What matters is the structure of the category. And whenever mathematicians use a name of something, they should really define it so that we all know what we're talking about. And it's a bit difficult with a category because you have to say what the objects and the morphisms are. So, for example, the categories, we talk about the category set, which usually means the category of sets and functions. But we don't mention the fact that we're just thinking about functions. It's taken as read because that's the most natural form of thing for morphism to have. There are other categories derived from the category of sets, like you might have the category of sets and bijections, or the category of sets and injections or something, in which case you're more likely to have to do something to the name of the category to make sure we're all clear what the morphisms are. But, for example, in France, this category is known as ENS because that's short for the categories, the sets in French are called les ensembles. And so French mathematicians will refer to it as the category ENS. So the important thing is always that we're clear what category we're talking about and what name we're using. Okay. Next question about the definition of a category. Should we interpret all arrows as having labels, but sometimes we don't show them because sometimes they're not immediately relevant? I think yes. I think that the label of an arrow isn't really the point of it. The point is what it is, and we can label it with various different things. But what's important is what it does, not what it's called. And the whole time in category theory, it shouldn't ever really matter what anything is called. What matters is what it does and how it behaves. And when we're doing research in category theory, we just quite often make up letters for things as we go along so that we can refer to them to each other, refer to them when we're talking to each other. And we quickly run out of letters for things. And so sometimes we try not to use letters until we really need to refer to them because we keep running out of letters. Okay, next question. So there's a bunch of questions now about the set theory that's underlying category theory. So if you're not worried about this, you might want to tune out, because my overriding message is that it isn't really necessary to worry about a lot of set theory when you're doing basic category theory. I will confess that I personally very rarely worry about set theory when doing category theory at all. And then when I do have to worry about it, I panic. Well, I don't panic, but I kind of freak out because I don't like having to worry about it. And I know that I'm not very good about it. And so at that point, what I do is I call a friend and I hope that the friend will sort it out for me. Honestly, that's what I do. At least I recognize when I'm likely to be running into an issue. But up until then, I don't worry about it. So first of all, does the formal definition of category rely on set theory? So this person says that they're noticing some words of set theory, such as elements of a set, or A and B are elements of something. And the answer is that it relies on some basic intuitionistic set theory, the concept of a collection of things, so that you can say what it is to be an element of those things. To do most basic category theory, it doesn't really matter, because it only matters when you're trying to avoid Russell's paradox. And basically, you need formal set theory to help you make sure you avoid Russell's paradox. So that's where the size issues come in, because once you start gathering together things that are large structures of large collections of things, you have to be careful that you aren't getting into Russell's paradox. So once you start having something like a category of categories, for example, then you have to make sure that you've used set theory correctly to avoid Russell's paradox. Now, the thing about Russell's paradox is that it is caused by having self-reference, but we get out of it not by forbidding self-reference exactly, but by putting restrictions on what gets to count as a set, so that then when you quantify, it's basically about what you're quantifying over. So if you say, if you put together too many things, then you get something that is strictly bigger, so that you can't then accidentally refer to itself. And so the main point is that there's a hierarchy of things of different sizes, so that if you take the collection of, you can't take a collection of all sets, because you have to always basically quantify over the elements of a set. So if you start with something that you know is a set, that is, it's kind of small, then you can say, I'm going to make a set that is based on that other set. So you always have to base all your sets on other sets. Whereas if you take, for example, the collection of all sets, you haven't based it on one particular other set. You've based it on all the possible other sets. And it's not that that's forbidden in set theory, it's that there's no way to do that. So no one sat down and went, okay, we're not allowed to do that. They just made a specific number of ways that you can build sets, and that isn't one of them. And so, so the next question, building on that, says, if I think of all sets, classes, and collections as bags you put stuff in, what trouble will I run into later on? And the answer is, if you're not doing very technical category theory, you probably won't run into any trouble. The place where you start running into trouble is if you're trying to do some very complicated calculations involving limits and colimits, for example, or something very technical involving collections of things, or I've run into it recently when I've been doing the Yoneda lemma. If you start trying to do functor categories between categories that aren't small, then you can possibly run into trouble. But I would say that for the rest of what's in this book, you're very unlikely to run into any trouble. And then the next question about size issues says, can we use the symbol for is an element of if the collection of objects is not a set? The answer is yes. You can still use is an element of if the thing you're thinking about is a collection rather than a set, or a large set, as is sometimes said. And then the final question about size is, how may the morphisms fail to form a set? What is an example of a self-referential collection of morphisms? Is there another way to fail to form a set? So this is what I was trying to say earlier, which is that it's not about self-reference exactly, it's about size. And so one way that the morphisms can fail to form a set, you can fail to form a set if you've constructed them out of something else and there's too many things. So one example, right, so I said that if the collection of morphisms between any pair of objects is a set, then that's called locally small. So it might be that the total collection of morphisms isn't a set, but that's still okay as long as, given any pair of morphisms, the collection of morphisms between those is a set. And that's called being locally small. So to get a situation where the collection of morphisms between any given pair of objects isn't a set, one typical example, let me get my screen back again, is the category of spans. So the objects are sets, and a morphism A to B, and I'm going to write it with a little line through it to show it's a bit strange, is what's called a span. So a span is where, rather than mapping straight from B, you have a set up here and it maps, you have a pair of legs mapping over there. Now you have to do something a bit tricky to make that into a category. Naturally, it's a bi-category. That's a higher dimensional thing because it's only weakly associative. You possibly could make it strictly associative, but the point is now the morphisms from A to B involve all possible sets, because you could put any set up here and manage to get yourself a function from A to B. And so the collection of morphisms from A to B is sort of the order of magnitude of the collection of all sets, and that's not a set. So that's definitely something that's going to be not small. Another example, I just looked this up honestly to see what some typical examples are. Another example is it's from homotopy theory, where you are trying to, and this is going to be a bit too complicated, but someone asked, so I'll say it's from homotopy theory. So if you're trying to formally invert some of your morphisms, then you can't invert them, but what you do is you make a zigzag of morphisms from one place to another. And then you make a new category where the morphisms from here to here are all the possible zigzags from there to there based on the original category. And the thing is, there could be loads of those. And so that apparently, I just looked this up, so actually I'm just quoting the internet, is something else that is typically not locally small. But a lot of categories that we end up working with that aren't small are locally small, so that's okay. For example, the category of sets itself, the collection of objects is all the possible sets, and that's not a set, right? That's a classic example of something that is too big to be a set to avoid Russell's paradox. But given any two sets, the functions between them form a set. And so that is locally small. And because a lot of categories are based on the category of sets, a lot of them will end up being locally small, like the category of sets. So, but in summary, I would like to say, really, for now, it's not something that I think you definitely don't need to worry about it. If you want to worry about it, then go ahead and worry about it, but I'm not going to worry about it very much in this book. Okay, next question. Does associativity imply that composition with the same extreme endpoints are the same? It depends what you mean by that. So there could be two different morphisms with the same extreme endpoints going through completely different places. So there's no reason that those two composites need to be the same. But what it means is that if you take the same string of morphisms between the same endpoints, then yes, any way of composing those will be the same. The formal term for compositions with the same extreme endpoints, well, it depends what you mean, right? So if you're just looking at compositions with the same extreme endpoints but could be going through something else in between, those are called parallel morphisms. But associativity doesn't say that all parallel morphisms are the same. It says that all different associations of the same string of morphisms are the same. And so that's what I would call that. And someone else at some point asked, what is a string? And a string is like a series. It's a series of things in a row. Okay, so then there's a couple of questions about the example of brother-in-laws. And I want to stress that I didn't define that category terribly formally. And so it's a little bit hard to make it precise because I just didn't define it formally. It was an idea rather than anything else. And so when there are multiple potential arrows from X to Y, is there a sense, and there's a sense in which all of the arrows can be considered the same? What's the procedure for defining this? And what is the merged arrow called? So I'm not quite sure. Oh, I think maybe I do see what you mean by a merged arrow. And so the point is, in the brother-in-law situation, we had two ways of going around a diagram that looked like they might have been different, but they produced the same word in the English language. But you could say they still went around different paths. And so in some sense, that's a kind of feature of the English language rather than anything else. There are situations where you can decide that you want to force some morphisms to be the same that weren't originally the same. So if the two ways around here weren't the same, and you decided you were going to impose a situation and you would be building a new category in which those two arrows had been made to be the same. And I don't know that there's a specific word for doing that, but what you would be doing really is imposing an equivalence relation on the arrows. So one example where we do that is in topology, where we look at topological spaces with continuous maps between them, but then we might decide that we only want to look at homotopy classes of maps rather than actual maps. And so in that case, we would we're putting a relation on the continuous maps so that we're saying that more of them are the same than used to be the same. I'm not quite sure if that answers the question, but I think that answers the question. So the next situation is, how does one resolve situations such as the ambiguity of this situation? For example, if we know that there is at most one arrow between any two objects, then we know that the square commutes. But how do we establish that there is at most one arrow between any objects? I'm not sure how to answer that question because it's so general. There are many different situations where there's at most one arrow between something and something else. Typically in category theory, well, typically in abstract mathematics, when you're trying to prove that there is at most one thing anywhere, what you do is you assume that there are two and then show that they are equal. And we'll come back to that a lot when we do universal properties, because we'll do a lot of needing to show that there is exactly one of something. And what we will do is we will show that there is at least one and at most one. So that's existence and uniqueness. And when we want to show that there is at most one, we quite often assume that there are two and then deduce that they are the same. So that is often a way that you show that there is at most one arrow from something to something else. But sometimes it's really inherent in the definitions. And so if your arrows are relations, then it's inherent in that definition that that's a true or false situation. And we quite often state that in the definition of a category by declaring that the morphisms are assertions. So you might say that a morphism from A to B is the assertion that A is less than B. And once you've said that the morphism is an assertion, then you know that it's either true or false, and there either is or isn't an assertion. So then you know there is at most one arrow from something to something else. I hope that helps a little bit. Does the commutative square represent two ways of doing things, so a thing, and they are the same? Yes. So here's if this square commutes, then what it says is that going this way is the same as going that way. Is that two ways of doing a thing? Probably. It's two ways of getting from A to C using arrows in the category. It might not always be, arrows in a category might not always be interpretable as doing a thing, but at the basic level, yes, it means that there's two ways of going around this square and they are the same. So the next question is, in the context of associativity and the existence of an identity, We are using the notion of equality in order to impose constraints. Is this notion of equality itself some form of categorical morphism? Oh, very good. So this is a question about equality between morphisms. So when you talk about associativity, you're talking about morphisms being the same, because you're saying that you've got 3 morphisms, and you're saying that H composed with G composed with F equals H composed with G composed with F. That's an equality between morphisms. And that's all we can say when we have a category, because we don't have any other way to relate morphisms to each other. And so this question is leading us into higher dimensional category theory, because higher dimensional category theory says, well, what if we want ways to relate morphisms to each other? Because category theory is already saying we should study everything via relationships, we might very well go, shouldn't we study morphisms via relationships? In which case that associativity shouldn't just be an equality, there might be a morphism between them. And that's how one way of getting started in higher dimensional category theory, where we say, actually, I want there to be morphisms between morphisms. And so in that case, we have objects, we have morphisms, but we have the possibility of morphisms between the morphisms, but that's at a different level. So this equality between the morphisms is not a sort of one categorical morphism, it's a 2 categorical morphism, because it is mediating in between 2 morphisms. So it is a 2 categorical, a 2-dimensional situation. And yes, at higher dimensions, that does cause problems. And we don't just want them to be equalities. We may well want them to be isomorphisms or even non-invertible things. An isomorphism is an invertible morphism. So that's a very, very subtle advanced thing. Thank you for asking that question. And someone says, are there categories whose objects are categories? And the answer is yes. We'll come back to that in the interlude, and I think it's in chapter 13, the one about large, it's in chapter 13, large worlds of mathematical structures. You do have to impose size constraints to make sure that you don't have Russell's paradox. And what would the morphisms of such a category be? Well, they're going to be morphisms between categories. So I won't preempt that chapter by saying what it is now, but it's a wonderful exercise for you to think about what you think a morphism between categories should be. Think about the structure of a category. Think about what would happen if you had 2 of those things and how you could possibly map from one of them to the other, and what would be a sensible way of doing that. So finally, someone says, this was such a beautiful example of commutative diagrams. The context is so far from the way I've seen them in the past that it snuck up on me. Thank you. I don't know which example you're talking about, but I'm glad there was an example that you liked. And finally, some praise. Thank you so much for this book club. Thanks a lot for your great work. Thank you. I love your books. The word drum roll on page 102 is so cute. Oh, thank you. I really felt like there'd been such a long build up to the definition of a category. And I know there are a lot of category theory books that are trying to be accessible, but they start with the definition of a category. And I wanted to have this build up. And I feel that when I'm teaching my students in the School of the Art Institute, that we get to the definition of a category about halfway through the semester, and it feels really monumental. And so I'm glad that you've all made it here. It is going to get harder from this point, because now we're going to be doing more formal things, but I'm glad that you're here. Thank you all for putting this together. It's clear from watching the videos that you're all doing a lot of work to run this book club for us. I appreciate it very much. Well, we appreciate your appreciation very much, and we can keep going around like that as many times as we like. Thank you sincerely for talking these things through with us, and thanks, I'm having fun. Thanks, I'm having fun too. So the next few chapters are quite short, so the next videos will probably almost certainly be shorter than this one, and I hope that that will give you a chance maybe to get a little bit ahead, because things will get harder after that. We may find that we need to take more than a week on some of the future chapters, we'll see, but so far I think this is going really well. So congratulations, everybody, on making it to the end of the first part of the Joy of Abstraction. And thank you for submitting your questions. This is going so well, I think, and it is definitely fulfilling and exceeding my hopes for how this book club would go. So I'm so glad to see so much engagement and interaction. And thanks again to the Topos Institute. And I guess I'll stop my screen share so that we can finish without that being such a tiny screen. Thank you, everyone, and see you next week with chapter 9. Bye.